Good morning. In the last class, we have dealt with ESR, electron spin resonance. Electron spin resonance. What do you mean by electron spin resonance? It is a technique which is used the spinning property of an electron which are in resonance. We know that the molecules has atoms and it has nucleus. Nucleus has protons and neutrons. Around this it has electrons. Electron has both the spinning property and orbital property. When a charged body rotates, it will create magnetic field. So it behaves like a magnet. In the last class, we have discussed all these matters. As a summary, we can say in ESR only paramagnetic electrons that are used. So ESR is also known as EPR, that is electron paramagnetic resonance. That is, in paramagnetic systems it has unpaired electrons. There is no chance of the self cancellation of the magnetic field. Okay. In this class, we have to discuss about the hyperfine splitting. Before going to the hyperfine splitting, we need to understand the total Hamiltonian of the systems when we place a nucleus in the magnetic field. If the nucleus is placed in the magnetic field, we know that nucleus has its own spin, that is denoted by I, capital letter I, and electron has its own spin, it is denoted by S. If these two interact, that is nucleus interact with the electron, we will get hyperfine splitting. In addition to this hyperfine splitting, if the electron spin in the presence of the magnetic field, this electron spin individually split, we will get ESR lines. Okay, in hyperfine structure or in hyperfine splitting, there is the possibility of the there is the interaction between the nucleus and the electron spin. In addition to this, electron spin split into ESR lines in the presence of the magnetic field. If this interact with the nucleus, we will get hyperfine splitting also. Okay, that is, hyperfine structure occur as a result of the magnetic interaction between electron spin, capital S, and nuclear spin, that is denoted by capital I. Interaction between S and I. Due to this hyperfine structure, ESR signal or this peak again split into several lines. From where we will get this ESR signal? That is, if the nucleus, that is, if the nucleus has the if the system has the unpaired electrons, it has the spin, that is, this electron spin is individually split into the ESR lines in the presence of the magnetic field. This ESR signal again split into several lines due to the hyperfine interaction, that is, due to the interaction between the nucleus and the electron. Okay, now we are going to discuss about the total Hamiltonian, that is, the total energy occur if the nucleus interact with the electrons. Obviously, there is electron kinetic energy, that is minus h square divided by 2m delta square, and it is internal potential energy, that is denoted by V0, and there is crystal potential, that is crystal potential if the atom or molecule is under the environment of the crystalline environment, that potential is known as crystalline potential, that is denoted by V crist. Okay, if the splitting is occurred, due to this splitting, if the energy level split due to this potential, that is due to this crystalline potential, that splitting is known as fine structure splitting. Okay, in the case of the free radicals in solutions, this contribution is almost zero. And next energy is electron Zeeman energy. That is, here the interaction between the electron spin magnetic moment mu s and the external magnetic field. Interaction between mu s and B. And again the nuclear Zeeman energy, that is the interaction between the magnetic moment of the nucleus with the external magnetic field. Okay, that is denoted by I, and Gn is the nuclear G factor, and mu n is the nuclear magnetron. And the next energy, that is the very important energy, that is nuclear electron spin coupling. Here we will get hyperfine interaction, that is hyperfine structure, and we will get hyperfine structure. And in this we will have the two additional terms, that is nuclear electron spin coupling, that is the coupling between the nucleus and the electron spin, and the another is the Fermi contact term. Okay, and this energy is entirely depends on the angle between the magnetic field and the line joining of the dipoles. Okay, that is the nuclear electron coupling, that is a direct dipole-dipole interaction between the electron and nuclear magnetic moments, that is nuclear electron coupling, interaction between the nuclear magnetic moments and electron. Okay, so and it is depends on the angle between the magnetic field and the line joining of the two dipoles. So it is completely directional, and we can say it is anisotropic interactions. And this hyperfine interaction is mathematically written by these equations. Here this hyperfine interactions, that is proportional to 1 by r cube, where r is the distance between the dipoles. Okay, and this second term, that is the Fermi contact interactions, that is the interaction between the nuclear moments and the magnetic field produced by the electron spin at the nucleus. Okay, this is the interaction between the nuclear moments and the magnetic field produced by the electron spin at the nucleus, that is the Fermi contact interactions. This this interactions is just a minute. Yes. Okay, sorry for the inconvenience. This interactions is denoted by these terms here. Psi of 0 is the electron wave function at the center of the nucleus, and A is the hyperfine splitting constants. And there may be the chances of the other interactions, that is electron spin orbit coupling and nuclear moment in electron orbital coupling, that is electron spin and orbit coupling, and another is nuclear moment and electron orbital coupling, and the next one is electron orbital and magnetic field coupling, and the last one is the nuclear electric quadrupole energy. Okay, this nuclear electric quadrupole energy is significant only for the cases of the nuclei which has the nuclear spin is greater than half. Here we will deal with I equal to half systems, so we can avoid this electron quadrupole energy. Okay, now this hyperfine interactions, hyperfine structure. And this hyperfine structure is due to occur as the result of the magnetic interactions between the nuclear spin I and this electron spin, that is interaction between S and I. Due to this hyperfine structure, this ESR signal again split into several lines. Here we are going to discuss about hyperfine splitting of a hydrogen atom. We know that hydrogen has one unpaired electron with a spin S equal to half, and one proton with nuclear spin is half, that is S equal to half and I is also half. So MS equal to plus or minus half and MI equal to again plus or minus half. In the absence of the field, these electron spins are degenerated, that is there is no splitting. It has all the energy levels have the same energy, that is electron spins are degenerated. But in the presence of the magnetic field, all the electrons spin split into two levels, plus half, minus half, and both the energy levels plus half and minus half interact with the nuclear level to give the hyperfine structure. Okay, that is in the presence of the magnetic field, these electron spins which have, that is it the levels, that is plus half and minus half, and both the energy levels interact with the nuclear level, that is interact with the nuclear level to get the hyperfine structure or hyperfine splitting. We can see the energy level diagram. See, here there is no field, there is no splitting of the spectral lines. If we apply the magnetic field, there is the splitting for plus half and minus half, that is this electron Siemens energy splitting, and due to the interaction with the nuclear spin, it again split into four lines, that is here one transition, here one transition, that obeys the selection rules, that is delta ms equal to plus or minus 1 and delta mi equal to 0. Obeying these selection rules, we will get two transitions. One transition is from minus half to plus minus half, another is from the minus half to half. So we will get two signals. Okay, this is the energy levels and allowed transition for the hydrogen atom. Okay, here we neglect the case of the nuclear spin interactions, that is here we consider the total energy. The total energy is H is equal to this term. This term is for the electron Siemens energy, and the next term is for the nuclear Siemens energy, and the fourth term, sorry, and the last term is for the that is a hyperfine interactions. Okay, and neglect all the energy terms because that are insignificant, because and here this the second term, that is the nuclear Siemens energy term, that is the value is almost, that is approximately 2000 times smaller than the first term. So we maybe neglect this term also. Okay, so the total Hamiltonian, we will get the total Hamiltonian is equal to this term, that is g mu b b dot s, that is from the electron Siemens energy, and summation ai li dot s, that is due to the nuclear electron spin coupling, that is the hyperfine, that is the this term is for the hyperfine structure, that is hyperfine splitting or nuclear electron spin coupling, where A is the hyperfine splitting constant. Okay, thank you.